So the last quantity that we want to introduce, that again is very analogous to something that we talked about with translational motion, is angular momentum. And so angular momentum is going to be the rotational analog of the linear momentum that we talked about a couple of weeks ago. So we said the linear momentum of a particle is given by this expression. The linear momentum p is equal to the mass of the particle times that particle's velocity. That momentum is a vector quantity which points in the same direction as the velocity, and its x and y components for the problems we were going to work where the object could move in two dimensions was given by the x component of the momentum is equal to mass times the x component of the velocity, the y component of the momentum is equal to mass times y component of the velocity. So the angular momentum for a rigid rotating object, so these are our extended objects, not point masses, but our extended objects now. That angular momentum, we're going to use the letter capital L to represent the angular momentum, and that's equal to the moment of inertia times the angular velocity of our object as it rotates. Because the moment of inertia cares about the pivot point, angular momentum also cares about the pivot point. Angular momentum is a vector quantity. It points in the same direction as the angular velocity vector. For the problems we're going to work, where our objects are rotating objects, we're going to be able to draw in the xy plane. That means that the angular velocity vector is going to point along the z-axis, so into or out of the plane, which means the angular momentum will also point into or out of the plane along the z-axis. So we'll have a single component equation to describe the angular momentum, and because that's a one-dimensional problem, just like the rest of our rotational problems, we're going to make sure that we focus on signs and get the right sign in thinking about the angular momentum as a vector quantity. So of course, to get the right sign, we've got a right-hand rule. And so let's take a uniform, long, thin rod that's rotating clockwise about its center of mass. And again, we know from using our right-hand rule that if I take the fingers of my right hand and curl them so that they curl clockwise, the thumb of my right hand is pointing into the screen, which tells me that the angular velocity points into the screen here, into the page. Well, since I know that the angular momentum points in the same direction as the angular velocity, if I know the angular velocity points into the page, that means the angular momentum must also point into the page. So if I have an object rotating clockwise like this one, then its angular momentum is going to point into the page. An object rotating counterclockwise, if I curl my fingers counterclockwise, my thumb now points out of the page, so the angular momentum for an object rotating counterclockwise would point back up out of the screen towards me. Units of angular momentum. Well, again, if I calculate angular momentum by taking the moment of inertia and multiplying it by the angular velocity, then I get the units for angular momentum by taking the units of moment of inertia and multiplying them times the units of the angular velocity. Moment of inertia has units of kilogram meter squared. Angular velocity has units of radians per second, and again, we're going to take advantage of that property of radians, that when we don't need it, we don't have to bother writing it. And so we get that the units of angular momentum are kilogram meter squared per second. Much like what we saw with the linear momentum, even though in some sense it was the most fundamental quantity, we just left its units as kilogram meters per second. Same thing true as here. Angular momentum is arguably the fundamental quantity that we're keeping track of when we think about rotational dynamics. We don't have a special name for that unit, we just leave it as kilogram meter squared per second.